So I'm only going to give one example of an application of a cyclotron motion. And so this is going to be an application of cyclotron motion in particle accelerators. So let's look at this guy here a little bit. So there's a lot here, and I'm only going to touch on a few things. The world's biggest particle accelerator is at CERN. And what we find here is that electromagnets are used at CERN, at CERN's Large Hadron Collider. And a lot of the times they call this the LHC. Now, the Large Hadron Collider, I believe, came into existence around 2008. So it was built, right? It was built, it was built in 2008, and it took years to build it. So I don't know when they started building it, but I'm pretty sure it's 2008. So the electromagnets used in CERN's Large Hadron Collider are numerous. I mean, there are quite a few. So there are two kinds of magnets. Magnets used. One, they're called steering magnets. Okay, they're steering magnets. And that's exactly what we just talked about right now. So if you look at the steering magnets, I mean, if I remember correctly, the steering magnets are somewhere around 1,200 magnets around 10 to 15 meters long. And here's the crazy thing about them. They run around, I think it's like 10 to 15,000 amps. And these aren't the new ones. So these are the old ones. So what the steering magnets do is that they literally bend the beams. That's the whole goal. So their only goal is to change the direction of the proton beam. In other words, a positive charge beam. Now, as they get closer to the acceleration point, the collision point, they then have these magnets that are called focusing magnets. So I should be careful here. So when I say the steering magnets, they're typically dipole in nature. Focusing magnets I remember them being about 500 or so. So they have about 500 magnets, all close to the collision point. And these focusing magnets, sometimes you'll hear them called the final focusing magnets. But the key thing about these magnets is that they're not dipole. So a lot of these guys right here are dipole magnets. The focusing magnets are quadrupole. So, and I think these are quite interesting. So focusing magnets are quadrupole. And these guys are also long. I mean, I'm guessing that there's somewhere between 5 and 10 meters. And what they do here is that these focusing magnets, of course, they focus with the final, focus into the beam so that it increases the probability of collisions. Now, here's the crazy thing about this. So think about the energy usage. So if you're thinking about the energy usage, you're talking about that implies that we have about 1,200 plus 500 magnets at, let's say, 10,000 amps each. Well, that's a lot of energy usage. This implies here that this is a huge energy. I mean, it's huge amount of energy. And I would probably guess is that this is about the amount of energy to run a small to mid-size city. It's pretty crazy. So so when I looked at the CERN magnets, the picture was not great. So I'm going to use something that I'm very familiar with. This is the Stanford Linear Accelerator, and this is known as SLC, the Stanford Linear Collider. And and so what you're seeing here is that you're seeing a couple of things. I'm not going to look at the front of it, even though there's magnets there too, but what you're seeing right here is that right here, note how I have curvature right here. Note how I have curvature right here. These are the bending magnets. And their whole goal is to take the electron beam and actually bend it so that it could follow that path. And so when you look at this guy here, right here, this is the collision point. And what you're finding right before the collision point right here is that these are the focusing magnets. And the whole goal of a focusing magnet is to then just make the beam as small as possible. So if you were to go into the tunnel, it looks something like this. The beam is somewhere in here, and then you just have magnet after magnet after magnet after magnet. So let's look at this thing right here. So what does the bending magnet do? So the bending magnets are exactly what we've been studying. From the radius relation, we see here that the radius was equal to mv perpendicular qb, and what you're finding here is that this is proportional to the momentum divided by the magnetic field. And what you find here is the momentum in accelerators are unimaginably large for a single particle. So accelerators impart very large momentums to the charges that require extremely strong magnetic fields to bend them. So the magnet technology in accelerators is huge. So to give you a sense of this, a steering slash bending magnet is around 10 Teslas, which then tells you that if you compare the magnetic field of the magnet to that of the Earth, it's of the order of about 100,000. So it's 100 times stronger than the Earth's magnetic field. But this is old data. This information is old. And today's magnets are much stronger with higher currents. So they're now superconductors, which means that you need liquid nitrogen to actually cool them. So I don't know if the currents are a factor of 10 or not, but they're definitely larger than what I'm talking about. So just to give you an idea of a focusing magnet, it looks something like this here. Because I think the focusing magnets are what's really, really interesting. The focusing magnets are more complicated with quadrupole magnets. So what you find here is that they look something like this. So here's a magnet. So if I start to try to draw this to give you a sense, so the beam is right in here. So if you were to look at this thing, that's where the beam is at, right in here. So if you look at this thing, all I have to do here is just try to draw one of these. So let me see if I could make this drawing here. So I'm going to go. Then I'm going to copy this. So if I look at this thing, so what you're seeing here is that you have two sets of magnets. There's a coil here and here. So these are the coils that we're actually seeing here. These are the magnets. So if you run electric current through them, we're going to get that. So this is where these superconducting magnets are at. And now what you're not seeing here is that there's poles there. So to try to make the poles visible, by the way, they're there. I'm just doing this. This is an additional drawing. What you're going to see here is that these guys are now the poles. So when I look at this thing, what I want to do is that I want to copy this and then show you what these beams actually do here. They produce a magnetic field. So how does that magnetic field look like? Here, let me copy this so that I can, because I'm going to have to draw this a second time and I don't want to do that. So typically these magnets are right next to each other. And this is what happens. So this guy here is a north, north, south, south. And then the next magnet switches to south, south, north, north. So when I look at the magnetic field, what you're seeing here is that you're getting magnets that are doing this type of thing. And then you're seeing that the magnets are now sort of like spreading out like this. And so here's what happens. I have a beam that's coming in. So here's my beam. And what the final focus magnets do is that they do this. They come in, and this magnet is going to push these guys together here. So these guys are pushing the beam into a smaller bunch. But as soon as you do that, then there's going to be this guy is then pulling it apart. And so what you're getting here is that you get a smear of the beam that looks something like this. And so the whole point of the field here is to try to make this thin as possible. Now, when it gets to the next one, you've now switched, but the field essentially looks the same. but the poles have now reversed. So as they reverse, so what you're seeing here is that these guys are pushing in. Now these guys are pushing in here. So now if I look at this beam again, it's starting right here. And so now the next piece here is that this thing, let me draw this a little bit better. So I have a thinner beam, but we're trying to make it thinner. So now in this direction, it starts to spread out more. But now you're bringing these guys in, and now once again, you're pushing the bunch to get smaller. And if you do this a series of times, you can get the beam to be really small. And if the beam is really small, then the magnets, which is called the final focus, then increases the probability of collisions to occur.